So, what happens when a star in a binary system starts swelling up? To calculate this, we're going to have to use the concept of potential energy. Our gravitational potential energy is minus g m over r when you have a single object. If we plot this, we can plot the gravitational potential energy versus position, and we'll get something that looks a bit like this. Gravitational potential energy will be 0 a long way out, and then we'll drop and become very negative, and then we'll come back out and go back to 0. And that's what the gravitational potential energy looks like around an isolated star. What's happening? Well, let's say the star is quite a small one. Its gas at its surface will sit at a particular height in here. As the star starts swelling up and it turns into a red giant, surface layers require more and more energy, and they will move up and up. So the star might, at some later stage, fill this and get bigger. In principle, a star can get so big that it comes right up to the top and actually maybe starts spilling over like that. But it's like filling up a bath. The shape of the star will just reflect the shape of the bath, with the level steadily rising as the star swells up. Now that's a single star. What happens if you have a double star? Well, in this case, if you do a plot of this, gravitational potential energy versus position, you get two of these terms, one centered on the red star, one centered on the white dwarf. So what you get is a curve that looks something like this. Might be 0 at some distance, and then it drops down for the red star, then it comes up, and then it comes down for the white dwarf star, and then it goes back out again to 0. So now what happens when a star swells up? It might move up and up and up and up here. This time, if the energy goes up over a certain level, the material will start spilling down into the potential well of the white dwarf. In principle, it could fill up to both levels and give you a sort of a double lump star, but in practice the matter falls down to the surface of the white dwarf and gets very heavily compressed down there, so it doesn't actually fill up the white dwarf's part of the gravitational potential. This is called the gravitational potential energy surface. We're just doing a cut through it. It's really a three-dimensional thing. There is one more complication, which is that in practice the two stars are orbiting around each other. So we have to allow for centrifugal force, which actually it turns out makes this curve down a bit outwards. That means when stuff gets to a certain distance, it gets flung out by the rotation centrifugal force. Centrifugal force doesn't really exist. It's just an artifact of the fact that we're measuring things in a rotating frame of reference, and we'll come back to that frames of reference later. So this is what's called the Roche surface. It's a surface of potential energy set by gravity and centrifugal force, and that tells us how the shapes of things change as they expand. It's really a three-dimensional surface, and we'll see a plot of that now. So what does this potential energy distribution look like? Here is a three-dimensional rendering of the potential energy, so the higher, redder colours are where the energy is higher, and the blue is where it's lower. And you've got the two stars here, and the whole surface.
That's very pretty. I kind of like doing it as a contour better so you can see in more detail what's going on.
Okay, so let's have a look at a contour plot of the same thing.
That's much better. So here, this is sort of like a topographic map, and so these are essentially how deep the holes are that you just saw, and these are these little potential places where you can see there's like these little plateaus. And these plateaus, when you have two things orbiting themselves, are very useful. For example, putting spacecraft there, because they don't like to move when you put them. We call these the Lagrangian points. But it also shows that if you look, there's sort of a saddle. If you think of these being two holes, there's a saddle point where if you make things too big, material is going to leak from here to there across the gravitational potential.
So this is the bigger potential well, so that's presumably where the white dwarf is, and this is presumably where the red star is, and we just talked about it. Maybe it swells up at the end of its life, and the gas is going to leak out, and where's it going to leak? It's going to leak across the saddle and come down here.
Yeah, so imagine that as this star starts using up its fuel, and it gets bigger and bigger, well, if it's just within its own little well, nothing happens. But what happens when it leaks out through here? It gets bigger than that. then it's going to want to fall down there.
And it's not going to fall straight in, because remember this whole thing is rotating around. It's got angular momentum, so it'll spiral in some complicated pattern and probably end up forming a ring or a spinning disc.
And that's because we have to conserve angular momentum, and just like the ice skater who starts spinning and they bring their leg in, they spin up, this stuff is going to be doing the same thing.
And so at last we can put all the pieces together and come up with something that both makes theoretical sense and kind of fits the data.
All right, this actually looks like something I can almost relate to, Paul.
Yes, we've got the red star, which has expanded because it's going to end its life until it's filled what we call the Roche lobe, this potential thing, and the gas is spilling over.
And so that's the little bridge between the two potential well holes.
Yep. And as it falls in, it gets deflected to the side because of conservation of angular momentum, until eventually it crashes into a spinning disk. And where it crashes into it, we're getting a hot spot, because suddenly you get this column of gas falling down, it's gaining gravitational potential energy as it falls down the potential well. It smashes in and hits here. And it smashes into something, and it's only see that emission from the far side. That's giving us our opaque flashlight.
And presumably the material isn't just coming in nice and gently, evenly. It's coming in bits and pieces, so you get a flickering of the material.
Yep.
And that material, that disk of material, is made up of, many, many years worth of stuff coming in and spinning up. And so it's sort of a residual from what's happened in the past.
Okay, so let's see if we can work out what the physics of this actual disk is.